people look at a, you know,
Yes, I'm here.
Thank you for all visitors of the class, because it is we all are very pleased to show what students achieved during half a year, and probably class attendees will be happy to answer unexpected questions. So this is CHEM676/676 Introduction to Computational Quantum Chemistry course, and this is for both graduate and undergraduate students. The course did have 4 goals: to provide theoretical background in computational chemistry to share the basic practical skills of modeling materials and modeling, and two more goals: to apply the skills to practical problems, and the goal number 4, scientific communications. So attendees of the class were already practicing and testing and being examined on their abilities in sections 1 and 2 in theoretical background and practical skills. And today's meeting is basically on bringing their new skills into real life. There is a hope that these skills will be later successfully and beneficially used for research projects of their primary investigators and towards their degrees. So there will be 8 talks. They are symbolically split on the 3 sections. So functional materials, nanostructures, and catalytic reactions. It's enabled is spent minutes on each presentation, and to enable whatever is needed, but no more than say 3-4 minutes for questions. So speakers, please try to be brief. Being brief is good for today. Another little advertisement. If you are not speaking, if you are not the speaker and you are not asking the question, it is advised to mute the microphone. It will enable higher quality of transmission. But if you are speaking, please do enable microphone and camera. So there will be slides transmitted from this station. So the speakers are invited to give voice messages, like next slide, when it will be time. So with this, I would like, and before we start, I would like to acknowledge support of College of Science and Mathematics at NDSU, the CCAST Computational Center at NDSU, and NERSC, Department of Energy Center, as well as National Science Foundation grant. So with this, I would like to invite the first speaker, MD Mozammal Kamal Raju, to the stage. Raju, please test the mic.
Yes, can you hear me?
Yes. Okay.
Okay.
And
thank you, Dr. Dimitri.
Okay, and let me bring your first slide. Okay. I'm stop watching in 5 minutes.
Okay, thank you everyone. Study of structural and optical temperature. Previous slide, please. Yes. The title of my project is Study of Structural and Optical Properties of Cubic LLZO with the change in temperature using first principle calculation. So I am the presenter, MD Mozammal Kamal Raju, and course instructor, Dr. Dimitri. Next, please. So in the introduction, we'll discuss why we need to study this project. So day by day, with the increase in population and the number of modern industry, the demand of power is increasing. As a result, but we are losing our natural resources. So as a result, we are looking for energy storage devices, lithium and battery, and which is solid, and LLZO, the lithium oxide, the room temperature, and which has very low ionic conductivity, order of 10 to the power minus 6 Siemens per centimeter. And the another one is cubic phase, which is stable at higher temperature, generally more than 400 Kelvin, and which has a little bit higher ionic conductivity, as you can see. Why this study is important? Because the synthesis process for LLZO is sintered at higher temperature. Generally, it's sintered at 1230 centigrade, so almost 1500 Kelvin. And this study will show the band gap and UV spectra analysis because this is the inherent property of materials. Next, please. So the method of calculation is DFT calculation. We use bar software, and we will use the and also for the total energy calculation, we will be using PBE-GGA approximation, and for the K space, we will use Monkhorst-Pack 1:1:1 matrix, and a cutoff frequency the initial system structure for our model. We have used 8 PFU, so we have used 8 combined cell as a unit cell, which has 192 atoms, where we'll be only mainly focusing on the blue. We have 56 lithium atoms here, but for these 56 lithium atoms, we have 120 available space in this unit cell, and which is the available space is for these lithium atoms come from 24D tetrahedral and also from 96H octahedral site. Next, please.
And Raju, you already spent 4 minutes out of 5, so please keep it.
So the result, and discussion. So thermal stability. So for the thermal stability, you can see first of all we have to look: is it the model is stable with thermal position when we increase the temperature? For the elevated temperature, you can see the graph is almost constant with the time step. So if we do the more time step, it will be more. This is for 500 times. Total energy is decreasing. The band gap is decreasing with the increase in the temperature. So this is the graphical view. So if we go next slide, you will see the tabular form. Next slide, please. So the band gap is decreasing from 4.37 to 2.41. This is going to very high band gap semiconductor, and also the total energy is decreasing because the kinetic energy is converting to the potential energy is converting to kinetic energy, and it is converting into heat. That's why the total energy is decreasing. Next, please. Also, you see the optical property, and you see the it's shifting from left to right. So it's going flatter from left to right. So this potential because and you see at the higher temperature at 1500 K, there comes a extra lobe. That's the with lower amplitude, which is clear the indication of the ionic movement and the broken bond for our model as we increase the temperature. Next, please. Previous slide. We skipped one. Actually, okay, it's okay. So we skipped one slide. It's okay. So this is the interatomic distance for our model. So if you see the very first one, this is for at the 0 Kelvin, and the number D is for the 1500 Kelvin. So you see there are the spikes are clearly visible for 0 Kelvin. That means the atomic bonds are clearly there. But as we increase the temperature, the spikes are getting flatter. That means the more bonds are breaking, and this indicates the atoms are getting closer, and this indicates the electronic transition possible at lower temperature. Next, please. So as we increase the temperature, our ordered geometry become disordered, and this is the clear indication from this figure. So number A is for 0 Kelvin, and number B. Next, please. You will see as you can see, this we just extrapolated the mechanism from our simulated results, and the consideration because this is simulation process. And from lithium ion is changing their position from one side lithium ion conductivity of cubic is higher, getting higher. Next. The main thing is to get a disordered geometry, and we can get it by creating vacancies, interstitials, or doping, which can be a further research study plan of our this course. Thank you, everyone.
So presentation is open for discussion.
Hi, can you hear me?
Yes,
Hello?
Dr. Hong.
Oh yeah, okay. So it's a nice work. You are very brave because it's nice. And it's a good exercise for the course. Now, if you are thinking about from the research side, there are lots of issues that you should pay attention to. The first one is the band gap that you calculated is significantly lower than the actual band gap. The band gap of LLZO is about 6 electron volt.
Yes.
And the largest value you got about 4 or something. And that's common calculation. The problem is, I then determine band gap, using the calculation that you do. I mean, it's very tricky because you don't have a ground state structure, right? You do MD simulation, every atom's moving around, and then you look at the density of state and you identify the band gap value. I mean, be careful with that one.
allocating
should be a little quicker.
Okay, sure. Everyone, my topic is the effect of heat on the properties of cellulose nanocrystal by utilizing the density functional theory. Next, please. The cellulose is the most abundant and renewable biopolymer, which can be extracted from a lot of sources like the wood and cotton. And due to its lower cost and excellent mechanical properties, cellulose nanocrystal has been used in a lot of applications like the energy storage, reinforcement, or electronics. So here is a schematic figure show how the molecular structure of cellulose nanocrystal looks like. And the unit cell in triclinic lattice tab has been used for computational model. The geometry optimization first to make sure the local energy minimum status, and then the heat is applied from 300K to 1000 K. For cellulose nanocrystal, the melting temperature is around 600. So we choose three typical temperature, well below the melting temperature, approaching, and even well above the melting temperature. So the project is trying to have a molecular level understanding of how the applied heat will influence the conductive properties of cellulose nanocrystal. At the same time, we also look at the molecular dynamics at 300K and even high temperature. Next, please. To get started, let's look at the absorption spectra first. At functional the geometry optimization. Electron absorbed to move on to the next orbital. For example, the first transition energy peak is around 3 electron volt, which indicates the transition from the HOMO. Also, this value is consistent with the band gap, where and we will show absorbed from the density of states. We will talk about later. And the first peak here also corresponds to the last peak of the absorbance, where the wavelength is around 550 nanometer. The absorbance also can be used to describe the optical properties, just as Raju said, and also the color matters. Moreover, here is an illustration of HOMO and LUMO orbitals after geometry optimization. As you can see here, the occupied orbital, which in blue, is primarily localized hydrogen atoms. However, the charge density tends to be distributed on the negatively charged oxygen, which corresponds to the red domain. Next, please. And then let's move on to the density of state. So the shaded purple region refers to the occupied or the valence band, while the empty area corresponds to the unoccupied or the conduction band. So the narrow band gap here is around 2.3 electron volts, jump from HOMO to LUMO. So in order to look at how, whether the elevating temperature will influence the band gap of the CNC, I just summarized all the which apply the heat from the 300K to 1000 K. Dr. Katie, can you click and I'll show a table here. So I just summarized the band gap information in this table. If you look at the first and the last column, actually there's no obvious correlation between the temperature and the band gap. Probably due to the reason that the cellulose nanocrystal is kind of insulator. Probably there's no significant correlation between the temperature and the band gap comparing to the semiconductor, where the band gap would decrease with increasing the temperature. Next, please. We further investigated the radial distribution function for different types of atoms at a wide range of temperature. The RDF here describes how the density varies as a function of distance from a reference particle. Actually, there's no big difference at lower temperature. However, if you look at the red figures, the figures on the right side, the peak become broader, both for oxygen to oxygen bond and carbon to carbon bonds, which indicates the increasing degree of morphization. Moreover, the intensity is at a high temperature is pretty lower than the intensity at a lower temperature. I feel like probably due to some breaking of bonds, because the at high temperature the CNC is kind of in melting state. And also I showed two short video. Dr. Killing, can you click it? Yeah, if you look at the detail, there is two short videos showing how the atoms looks like at 300K and 1000K. Yeah, if you look at the right side, actually there is a bond breaking and reforming phenomenon at the 1000K, where the temperature is well above the melting temperature. Then I just also show some molecular dynamics at different temperature. It's very similar to Raju's work at a lower temperature. Then mobility move further. Next, please. So just due to recap, and there is no obvious correlation between the band gap and the elevating temperature. But from the RDF, we can know that at even high temperature, it shows the increasing degree of amorphization. Thank you for your attention. Thanks. Any questions?
Okay, let's thank Zhaofan for presentation. And, it's open for discussion.
The temperature
right, but I mean, you're at 1.86 for your band gap, and you do 2. I mean, to me that says something. But again, maybe I'm wrong. So I mean, but I'm just curious.
Yeah, I just check. I mean, that you add 3 different temperatures. Also, I just run one case. Probably, if I can run more cases at different temperature to have a more understanding.
Well, I mean, and you think about in real life, an experiment, we would be doing temperature.
Realize in the real experiments, to test the real cellular nanocrystal in the experiment.
Zhaofan, let me contribute to discussion and check your opinion on the would the band gaps stay the same or change if you use simulation cell with more than one unit cell? Could there be a trace of spurious interactions between the simulation cells? system, but unlike the previous, which has some specific properties. So, Amir, do you have microphone?
Yes.
Okay, so floor is yours.
Engineering. Today I'm going to bring the conductivity of to regulate some thermal and mechanical properties of these materials. Usually these materials are very interesting because they are useful because their behavior can be manipulated by some additives or changing the side chain. Recently, as you can see in the bottom figure, we investigate the thermomechanical of this polymer via coarse-grained molecular dynamic simulation. Now we want to explore the activity of this material via and density functional theory. Next, please. This is the computational model that we defined here. The polymer for study. It consists of two monomer that composed of dimer, and for the side chain we have C6 and C8. They are alkyl group, means there is 6 carbon, also 8 carbon in each alkyl group. Next, please. And this is the snapshot of the conjugated polymer model. Next, please. As it is mentioned by Raju and also the Zhaofan, the maybe most important material. As you know, for the semiconductor materials, we expect to have a band gap between 0.1 and 3. Usually, this value is reported between 0.8, according to my best knowledge, to 1.8 for the conjugated polymer models with different structure. Here, at the room temperature, the band gap is observed 0.89 electron volt for this conjugated polymer model, as you can see in the top left figure. Also, the top right figure shows the spectrum absorption. We expect from this plot that the first peak should fall into the band gap, and as you can see, it's around 0.9 for this polymer model. Next, please. Also, for this plot, if we have a momentum dispersion for frontier orbitals, we can extract some important information from this plot. For instance, if we fit a parabolic function, measure the sub gap that is near the zero, as it is highlighted in blue and red circles. Also, in the right column on the figure, the ME and MH, the mass of electron and mass of holes, is measured, and the relative values of ME are heavier than the MH. So one can qualify that the current polymer system is investigate the charge of the density from the frontier orbitals, HOMO -1 to LUMO +1. So for this is for the orbital 311, HOMO -1. As you can see, the maximum charge density appears on the oxidized pyridine group. So this localized state, as you can see in the top figure, this localized state is not conductive because the charge is not uniformly distributed. Next, please.
But for the HOMO, the maximum charge density resides on the oxidized pyridine group. This is a substantial density. There is a substantial density on each of the group, and as it is clearly mentioned, this uniform distribution of again, for the HOMO orbital, for the LUMO orbital, the maximum charge density here is on the oxygen from each pyridine group. So also again, similar to HOMO, there is a substantial density on each tyrosine and also pyridine group. So again, this charge density on each sulfur and tyrosine group that is uniformly distributed means that this state also, this delocalized conjugated state is also conductive. Next, please. And finally, for LUMO plus 1, again, it is uniformly distributed, but not uniformly. There is a delocalized charge, which is on the carbon in each group. But this system may be partially conductive, not completely. Next, please. Also, I want to show some brief results from the molecular dynamics at different temperature, as other guys discussed. For this conjugated polymer, we compare the DOS from for two different temperatures. Room temperature and also 100 Kelvin, and you can see by decreasing the temperature from 300 to 100, there is an increase in the band gap. That means that a decrease in the conductivity. Next, please. And this is a representative video from the molecular dynamic. If Dr. Killian play. This is a molecular dynamic at the room temperature. Next, please. That's just constant side chain length, but for the future study, I hope to continue this model and to see how
Okay, let's thank Amirhadi for and the
through
Yeah, for instance, in the I can say.
There are more questions typed. I mean, question after we finish the session, I will try to share questions and answers with all participants. But for the sake of time, let me invite everyone to thank Amir once again. So next presenter is her undergraduate program, and she was very brave.
Used for gas. Next slide, please. First, I want to introduce the model that has been used. Polyurethane is formed by removing of atoms from the a periodical model has been used the edges of the hole have been functionalized, and a gold cluster of 13 gold atoms has been embedded in the hole. Holy graphene is known to have many advantages, including high surface area, high electrical conductivity, and thermal and chemical stability, which outperforms intact graphene layers, and that's why we focus on that. Next slide, please. In this work, we have looked into its applicability for hydrogen sulfide gas sensors, which are commonly used in industry, primarily in oil refineries, wastewater facilities, oil and gas wells, and compressor stations. There it is important to keep track of the hydrogen sulfide concentration because it's a colorless toxic gas that causes adverse effect on the human body at low concentrations already. The model has been modified, like the model from the previous slide, has been modified by adding 25 hydrogen sulfide molecules above and 25 molecules beneath the whole graphene layer. And the computation has been performed by density functional theory that is implemented in the VASP software. And the PBE functional was used, and for visualization, we use VMD software. Next slide, please. And to start with the results, I would like to show the spin polarized density of states. On the left side, you can see the model or the density of states for the model without gas, and on the right side with the gas molecules. And on both models, you can see that there's no band gap, so the conduction band overlaps with the valence band. And in both cases, the model behaves as a conductor. And you can see when we add the hydrogen sulfide molecules, the energy of the HOMO shifts to higher energies, and the states closer to the HOMO consist of lower energies, while lower occupied orbitals have higher energy compared to the model without hydrogen sulfide molecules. And the Fermi energy for the model without gas molecules is about minus 2.4 electron volts. And with gas molecules, it rises about 0.8 electron volts to minus 1.6 electron volts. And we expect this change to affect the conductivity of the model. Next slide, please. Another observation is that when adding electrons to the system, the total energy decreases rapidly in the beginning and then slightly until reaching the minimum energy. And the model shows minimal energy at the oxidation state of minus 22. That means the model is most stable when 22 electrons are added to the system. And that means the system may attract negatively charged ions and electron donating molecules, for example, OH minus. And withdrawing electrons leads to an increase in total energy, so this is very unlikely to happen. Next slide, please. And the hydrogen atom from the from the bond between the sulfur and the hydrogen gets longer until the hydrogen bonds with the oxygen. And this is a very interesting transition, which will be subject of further investigation. And that leads us to the conclusion on the next slide, please. So we could show that holy graphene with gold clusters has potential to be used as a gas sensor for hydrogen sulfide gas. Will be conducted on electron donating mechanisms between the hydrogen sulfide molecules and functional groups on the graphene hole. How much the system attracts the negative charge could be compared to experimental data of zeta potentials of the model. And we could also see how different compositions of functional groups on the whole affect these. And all these may be possibilities to enhance the sensor quality, which is the ultimate goal of this research. And thank you for your attention, and feel free to ask questions now.
Okay, well, thank Rebecca for interesting presentation. And the talk is open for discussion.
I have a question.
crystal field splitting and spin orbit coupling. So what are perovskite quantum dots? Perovskite quantum dots are quantum dots or nanocrystals having the structure shown at the top right image. The mineralogist who found this structure left Perovskite, and so it has a formula of ABX3, where A is the monovalent organic cation, which is shown at the green. The sites in the image, and we have the halide anions, which are the red ones at the edges of the octahedral sites. And so they are very important nanocrystals because they offer a lot of important optoelectronic properties, including high quantum yield photoluminescence, and that can be used in variety of applications, including LEDs and solar cells. And they also offer a high degree of tunability by mixing halide anions, but because they are unstable in moisture. So a good solution for that would be the doping of the material, and the doping is basically introducing a small degree of impurity to improve the properties. So this will enhance the optoelectronic properties and make the nanocrystal stable as well. And manganese is actually a good dopant for this type of nanocrystals. And at the bottom right, you can see emissions. This is a photoluminescence spectrum for a doped lead halide perovskite quantum dots. And we can see two peaks in blue, of course, in blue, because the red one is the absorption, and we're going to focus only on the blue one, so the emission. And we can see the two peaks, the first one around 400 nanometer, which experimentally was measured, and that peak represents the emission from the perovskite quantum dot, and the second peak at the 600, around 600 nanometer represents the emission from the manganese, coming from the manganese. Next slide, please. So manganese is a metal ion having 5 ampere valence electrons in the d orbital, and so these electrons have orbitals looking like the one the first image showed at the top, where we have where we can see the orbital lobes for the 5 electrons in that orbital, and in the perovskite lattice, these halide anions, which in our case we used chlorine, Cl minus, which is considered as point charges. And react and especially in the 2 first orbitals that we can see there, the x squared minus y squared, and then the dz squared, which are directly on these axes where one actually will have a higher energy than the 3 other ones, and then this is called orbital field theory or crystal field splitting. So these 5 electrons in the d orbital would be separated into 2 groups where 2 of them would have higher energy and 3 of them would be when the manganese atom is or ion is in vacuum. So that's what you can see in the top right. Excuse me. Upon excitation, also the second concept that I will discuss here is upon excitation, the electrons revolving around the nucleus can create a magnetic field that will affect here are 88 atoms, including carbon, chlorine, hydrogen, nitrogen, and lead. And in the case of the dope model, we used 3 atoms of lead and 1 of manganese. And so DFT calculations using VASP software were used to extract the lower energy configuration during the geometry optimization, and compute the spin polarized density of state, and also plotted the partial density orbitals, or partial charge density orbitals, yeah, and I measured also the bond distances and angles. And I also want to note that n up down is defined as the difference in total number of alpha electrons minus beta electrons. It's going to be relevant in future talks and future slides. The next slide, please. So here in the data table, after the geometry optimization, the total energy of the undoped model, which is shown at the left, is minus 425, and then the other two total energies after energy geometry optimization was also included in the dope model for the dope model, and then the dope model after being excited. So in the first data table, we can see kind of like the energies are the same, right, for different bands. So the energy of the bands are the same, and the occupations are also the same, which would translate in very similar density of states plots that we will see next. And then in the second one, we can see that n up down is equals to 5, because from 132 to 136 in the one that's yellow, from 132 to 126, we have occupation in the alpha, and no occupation in the beta spin orbital. That will be directly connected to manganese contribution of the 5 electrons in the d orbital, which are having higher energy. And then in the third one, we have 3 extra electrons in the alpha orbital that are absent in the beta orbital for the same, talking about occupation-wise, and that would be due to the electron, one electron allowed to flip its state and then become negative, beta orbital. And so, yeah, well, we have 5 of them. One of them is going to flip and then be with the there is a very similar density of state plots. Here we can see the one alpha at the top, and then and beta spin orbitals at the bottom, with the valence band at the left and then conduction band at the right. And also we can see from the pictures of the orbitals, the orbitals localized at the chlorine ion, and then at the lead ion for the LUMO orbital. And also here the band gap was measured to be around 3.5 electron volts, which would correspond to an emission of around 354 nanometer, which is close to the experimental graph that I showed in the introduction, and that's around 400 nanometer. Slide, please. So for the dope model at the ground state, we can see that this symmetry is not present. So we have these 5 electrons contributed from the manganese, which are having a higher energy. This is represented by the higher, like the 3 last peaks in the alpha valence band. The 3 last peaks that we have there, the one we can see that this is not symmetrical, and then the 2 extra ones that are having higher energy. And so here we also confirmed the orbitals by looking at HOMO alpha minus 4 until HOMO alpha, to confirm the orbitals that were expected by the manganese ion electrons in the d orbitals. So here let's consider 2 scenarios when where n up done is equals to 5 when excited. So if it is equals to 5 after excitation, the band gap would still be, if you look at the LUMO alpha, the difference between LUMO alpha and LUMO and HOMO alpha, it would still be around 3.5, and that would correspond to an emission in the blue, the blue light emission that we saw around 400 nanometer. But then if the electron is allowed to flip, and then, if it's allowed to flip itself after excitation, means this electron from HOMO alpha would be promoted into LUMO beta. between a HOMO, LUMO beta, and the HOMO alpha would be around 5 or something like that. Around which the the previous one. And, but here, there's a lot of things that were not very much sure. So because I see that the LUMO alpha here has having less energy than the HOMO beta, and everything, I would have expected something closer to the previous one. But I try to compare the orbitals with the density of states and the energies to confirm that the orbitals contributed by the manganese ion electrons in the d orbitals, and we can see here that the HOMO alpha -2 is having that d z square, I believe, and yes, it wasn't very sure. So after that, what we did is measure the bonds and the angles of the chlorine, manganese, chlorine. And next slide, please. So here, I mean, in the previous slide, also the band gap was very small. Was very small, which would translate into a PL of close to 1,000 nanometer, which is not what we expected. So what I did was to measure the bond distance and the angles, and to understand if something happened during the geometry optimization or something like that. So what we noticed is that in the first one, in the one to the left, the angles were measured, and they were very different than 90 degrees, which is the configuration for the octahedral configuration, and different to 0.5 to like about 110 degrees. And to the right one, I measured the angle, the distances, the bond distances were measured, and then we see that the 4 closest nearest neighbors were around 2.3, but then after that we have another chlorine ion, which is 3.6 Armstrongs away, and then 4.6, which is even farther. So it looks like it kind of became tetrahedral during the geometry optimization, maybe. So, and next slide, please. So there is also a tetrahedral kind of, there's also the tetrahedral split. So ligand-filled splitting that can happen when the point charges or the ligands are attached, but not in the same axes as the orbital lobes that the orbital lobes are. So this would create also, I mean, it will still create this Coulombic environment, but the splitting would happen differently. So in this case, we're going to have three electrons orbital. The three electrons would go. That would be at higher energy than the two of them that were supposed to be at higher energy in the octahedral split. But then here also the energies is not, they're not as high as the octahedral one, because of course as as the orbital, as the lobes are closer to where the point charges are, there will be higher energies. There will be higher energy. So to understand the we use a more reliable assessment, which is the energy difference, which is just the delta energy in the total doped model and the excited state of the doped model. So we did the difference, and then it corresponded to a band gap of around 1.67, which corresponds to an emission of about 742 nanometers, which is which is closer to the emission. So to the emission that we saw experimentally. Next slide, please. So in conclusion, we understand that perovskite quantum dots have many applications due to their optoelectronic properties of high quantum yield, high color purity, and so we did the geometry optimization, spin polarized and stereostate, partial charge densities using the DFT with Comsham equations, and we also saw octahedral and tetrahedral splits as well, and we extracted the energy, and we confirmed that the PL was actually that the photoluminescence was redshifted. And so thank you very much.
Join in
to the
This is what we
means that there is no bleaching, there is no blinking, the lifetime. So it's a time-dependent process, and of course calculations do not
Thank you. So, like Dr. Killen said, my project was on the catalytic ability of just to answer some questions. Protons and is bound directly to the ruthenium. Next slide, please. So, looking at this slide, we can see as the charge changes from each, with the total number of electrons of each molecule. Those terms on the side, for example, stand for ruthenium ligand, and then a two-letter abbreviation for their the form the oxygen is taking. We can see that there's a dramatic drop in the level of total energy at the +2 and +3 charges, and then again at +4 and +5. But primarily what we have focused on in this occasion is the +2 charge of the ruthenium hydride ligand. hydrate ligand, sorry. Next slide, please. So looking here, we have a visualization of the HOMO and LUMO of the ligand, and what we can see here is that they are primarily centered around the ruthenium atom and the oxygens of the phosphite group that's attached onto one of the organic portions of the ligand. And so this is interesting, is that it's very likely some sort of hybridization possibly happening. As we will discuss later, we found that the reaction to remove and oxidize water occurred very rapidly under some rather non-controversial conditions, and it appeared that the phosphite group there played a significant role in affecting how it happened. Next slide, please. Really, the key of the entire presentation is a combined DOS diagram along with each of the orbitals that are representing. And what we can see here is that the LUMO is very, very close to the HOMO and has the ability to interchange between the conductance band and the observation band that you see with a very small band gap is very critical to being able to successfully make a usable catalyst as without between the different forms of the reaction in an efficient manner. Next slide. So, in form over a series of seconds, we can see that on the left, the phosphite the whole catalyst molecule. Slide. It's
Okay, please join me in thanking Stephen for interesting.
kind of
that means that actually it contaminates the catalytic agent, because my understanding is so
Well, that could certainly be a now. Is Yangchao, so atomic modeling of properties of carbon nanotubes. Next, please. I'm going to talk about three kind of different. So next, please. So for the first one is carbon. It has 94 carbon atoms, and the second one is hydrogen. There have 7 hydrogen atoms, and the third one is nitrogen. So there just have 1 nitrogen atom, and as you can see from the figure A, this is the initial state of this project is to study the energy, the density of states, and the absorption spectrum of the system at these 2 different static stages. So next, please. And study the density of states of the system when it consider the when the didn't consider the states. The density. Okay, next, please. I also studied the absorption spectrum of the system at 2 different stages. And as you can see from the figure, the absorption spectrum of the initial stage have a distinct peak before 4.5 electron volt, and the absorption spectrum of the final stage has no obvious peak, but just gradually decreases to 0 before 4.5 electron volt, and the absorption spectrum are 0 after 4.5 electron volt for both stages. So next, please. Then I studied the orbitals of the system at these 2 different stages. As you can see from the figures A and B, this is the orbitals of the system for the initial stage, and the figures C and D is the orbitals of the final stage. And we can find that the HOMO and LUMO orbitals are mainly located, at the CNT structures for the initial stage. But for the final stage, the HOMO and LUMO orbitals are mainly localized at the nitrogen atom. So the HOMO atom for the initial stage is distributed along the X direction, along the Z direction, as you can see from the figure A, and the LUMO orbital is distributed at the angle of positive and negative 120 degrees to the direction, as you can see from the figure A. The calculation for the initial stage of the system. Next, please. And then I also studied the orbitals of the system when it rotated about 90 degrees along the XY plane, and states are mainly next place. So the of the system when you consider the spin polarized calculation. So as you can see from the orbitals of the system of the initial state, and the figures BDF is the orbitals of the system for the final stage. And I want to mention that is this means the difference between the number of electrons in the up and the downstream component. Next, please. And we can find that band gap for the final state, and there is another band gap for the initial state, and the level of the initial state is just force within the gap in the spin up band, which indicating that the system have semi-conductor properties, and the Fermi level of the final state just falls before the gap in the spin up band, which means the system has the metallic properties. Next, please. And lastly, I studied the energies of the system when for these two different static stages. And as you can see, the impact of N up down energies at the final stage is significantly greater than that of the influence in the initial stage, and the changes of energy gap for the up and down spin components are basically constant. Next, please. So, in conclusion, in my project, I studied the energies, the density of states, and the HOMO and the LUMO orbitals of the system based on the Westra software package. And in the future, I think the absorption spectra and the orbitals of the CNT lead filter study when considering the spin calculation. Next, please. So last but not least, I want to say thanks to Professor Dimitri and the Department of Chemistry and Biochemistry for this wonderful course. And I also want to say thanks to all my classmates for accompanying me through this semester. And our WASP, VMD, Gaussian View, and Miller Lab for my project. Okay, thank you.
Okay, please join me in thanking Yangchao Liao. So Yangchao, please explore questions in the chat room because we need to give Mahek chance to present. And I would like to make a comment that what is presented as a final seems like an intermediate state because one of the nitrogen to hydrogen bonds is too elongated and it may create trap states inside of the gap. But your results for what you call initial seems reasonable. So please look for questions in the chat room. And I apologize that we didn't have time to go over detailed discussion. So let's thank Yangchao once again.
Thank you, everybody.
And the next presenter is Mahek Sadiq, who will explore applications of this materials of the course materials to bio-related objects. Mahek, are you online?
Yes. Can you hear me?
Yes.
And is based on the impact of Fe2 plus peroxidized lipid bilayer. Next slide, please. First of all, what is a lipid bilayer? It's a membrane surrounding a cell to protect the content of the cell, and it must be undamaged anyhow to protect the normal cellular and normal human body activity. Backbone and hydrophobic non-polar fatty acid needed in case of cancer, when we want to kill the abnormal cells from the human body to stop the mutation and metastasis, and we also need it in case of elimination of virus-infected cells. So when when a cell membrane is peroxidized, what happens is that it triggers apoptosis. And how is apoptosis triggered? A cell contains mitochondria, the powerhouse of the cell. When the cell membrane is damaged, the external foreign particles enter into the mitochondrial membrane, ultimately removing the barrier function of the mitochondria, initiating cell death. And in this way, the infected cells can be removed from the normal, healthy human body. Next slide, please. So, normally peroxidation can be done using hydrogen peroxide, but I want to focus on iron and peroxidation reaction. The second portion that is peroxide, the iron 2 complex reacts with that lipid peroxide, generating alkoxy radical made up of carbon, hydrogen connected to oxygen. That is alkyl plus oxygen. Is that initiate new peroxidation reactions? They attack new peroxides and initiate new peroxidation reactions by redox recycling of metal ions. So this simulation package fast, visual molecular dynamics to view the output, and video map to view the movie. Next slide, please. So the lipid bilayer that I focused working on is 1-palmitoyl, 2-arachidonyl, SN phosphocholine. So this is the structure of the PAPC. I didn't make it because I built the structure of a peroxidized lipid bilayer. That's on the next slide. Next slide, please. So what I made is peroxidized PAPC. That is 1-palmitoyl, 2,9-oxo, nanoenol, SN-glycerol, 3-phosphocholine, a monomer of this. So here the gray atoms represent carbon, the white atoms hydrogen, the red atoms oxygen, the orange one nitrogen. This is the structure of HOMO PC. Next slide, please. So that was the structure of the oxidized PAPC molecule, but I added iron Fe2+ aqua complex surrounding that HOMO PC. Fe2+ aqua complex surrounding the HOMO PC monomer. Next slide, please. So the equations that were used here, the Concham equation to view the electronic structure and to calculate the density, or total density of the structure, that fictitious density of the structures that I built. And another equation was for the electronic density of the states to view the electronic density at various intervals. And so these two equations were of importance. Next slide, please. So first, after building this whole structure and optimizing it in VASP, and then I heated the molecule. I heated the structure in two ways. First of all, I heated into 300 Kelvin, but no difference was observed. So then I heated it again to 1500 Kelvin, and a significant difference was observed in the bonds. Next slide, please. So the top one and the bottom one after heating. So we can see that there is no band gap. And yes, I did observe that the band gap difference was hardly of 0.2 electron volts. So yeah, so we can see that the shift of electrons from the valence band to conduction band, but there is no band gap here.
In thanking Mahek for interesting presentation. So it was very brave attempt to consider complicated biological object. Are there any quick questions if you are not getting disconnected?
Can I go ahead?
Yes.
So thank you.